Hey all, thanks for joining me again. This video is a little different. We're not going to learn a new physics topic. Instead, we're going to take a look at power plants. See a variety of power plants. There is a common theme in the types that we're going to look at, and most importantly, understand how they function on the general level and see how some of the physics that we've already learned is applicable, how it applies. Again, there's a wide variety of types of power plants. We're not going to get to them all. We're going to look at the most common way some of these power plants are creating electricity. They have very similar constructs, very similar ideas in how you actually get that electricity, but you could go into a rabbit hole and spend an entire sequence of videos on just coal power plants, for example. So instead, we're going to look at a much more general view of a variety of types. Here on the west side of the United States, where I make these videos, we don't just use one type of power plant. It's not correct to think that, oh, just the state of Idaho uses one type. There's a wide variety. We're not going to touch upon all these types here, but again, we'll look at kind of a subtype that has a very common feature in them, okay? Now, let's start with coal. We actually talked about coal power plants in a prior video that I made. Coal, its usefulness comes in the fact that coal burns very well, okay? Coal is kind of like a rock. It's not really. It comes from old, long dead plant material. But coal, just like paper, kind of like gasoline, it's flammable. It will burn if you light it on fire. It turns out, everybody, just because you have a pile of coal, that doesn't make electricity. The way we get electricity to be generated from a coal power plant is utilizing the fact that it burns very well. Let me explain how. Well, coal, you kind of start on, like, imagine this conveyor belt. It comes on in, this is like a big old chimney, and this is a big furnace. We light the coal on fire, so it is burning. It is obviously very, very hot. Fire by itself does not make electricity, not at least in the way that this power plant is going to utilize. Instead, the way we're going to use this coal and this fire is by making steam, all right? So inside this furnace, you see like this pipe that's kind of winding back and forth? That is pipes filled with water. So imagine you have a water source, like say a river or a lake. That water is pumped in. It's in pipes. It's not like we're mixing it with the coal. It is separated in pipes, but those pipes are snaking in the furnace with all that fire. And of course, you can imagine if I have this raging fire with these pipes nearby, the fire is very hot, it is going to heat up those pipes. That's the second law of thermodynamics, by the way. So the pipes and the water inside get very, very hot. That water, which was liquid in the beginning, heats up, it boils, or it turns to steam. And that steam is what's going to travel, and it's going to spin a turbine. I'll explain that process more in just a little bit. So really, we're using coal, not because coal by itself makes electricity, but because we can use it to burn things, to heat up water. That water will turn to steam, and that will spin a turbine and make electricity, okay? How? I have this silly little kettle gif right here. Obviously, in a power plant, this is much more intense, much more volume is being used, much higher pressures, but nevertheless, if you look at this steam from a kettle, it's kind of like wind. It is moving. It has a lot of kinetic energy. This high-moving, highly pressurized, very energetic steam will spin a turbine. When I say turbine, everybody, think of like a pinwheel. I know it's kind of a goofy analogy, but pinwheels are these little toys that will spin in the wind, or you can blow on them and it'll spin it around and around and around, okay? Think of a windmill. It is very similar in principle. This spinning around and around, well, that's important because here I have a turbine. It is connected to the generator, which has some magnets and wire. Spinning the turbine will, let's say, spin wires around magnets, okay? In real life, these turbines are gigantic. I do not know the source of this image, my apologies, but here it's showing a pinwheel kind of on steroids, and a generator in real life in power plants are ginormous. Again, I don't know the source of this image, so I'm kind of hypothesizing here, but maybe imagine there's a giant turbine in here, and imagine in this giant pipe, we have a lot of high pressure steam coming in. Now, if that high pressure steam is coming in, it will make the turbine spin, and it is going to spin wires around magnets. That's the general use. Now, why would we want to spin wire around magnet? Everybody, I hope you already know the answer to that. We've already gone over that. The whole reason we would spin wires around magnets is because we know that moving magnets or moving wires around magnets make an electric field, and electric fields move electrons. That's electricity. All the power plants in this video utilize this idea that I get a turbine, think pinwheel. I get this turbine to spin. It is connected to these wires that will spin around the magnets. That will generate electricity, okay? That's how a coal power plant works. Let's look at natural gas. Natural gas is a gas. It, again, comes from old, long dead like plant and living material, all right, from eons ago. But natural gas will come from Earth's crust. That natural gas will come in from underground. You might need to filter it, of course, but then natural gas, like coal, burns. So we light natural gas on fire. We don't take the gas and make it spin a turbine. That would be wildly inefficient. Instead, we light the gas on fire. That creates a lot of heat. We send water in pipes nearby. I know this is a simplified diagram, but maybe you're thinking that what I'm saying right now sounds a lot like our coal power plants. I have pipes going nearby this furnace that are filled with water. That water turns to steam. That steam spins a turbine that is connected to a generator. Geothermal power plants, they're a little nice because we don't have to burn anything. The hot water water is coming from inside the crust itself. Imagine like magma inside the earth. There are very hot regions. There also might be very highly pressurized sources of water in those regions. We can have that hot water get pumped up to Earth's surface. You can, based on how much water there is, how much pressure it's under, you can flash turn that water into steam, and that steam can spin a turbine, which is connected to wires. Moving wires around magnets make an electric field. Electric field moves electrons, okay? Then that water will cool back down, we'll put it back into the Earth, and that process can repeat over and over and over again. Okay, everybody, nuclear power plants. Nuclear power plants work using something known as nuclear decay, a type of energy that we have not talked about before in this class. The one we're going to talk about is uranium. There are other sources that you can use, but we'll just focus on uranium. It's a rock, or it's atoms found within Earth's crust. Uranium is a very large atom. It's so large, it's not very stable, and it will naturally break apart. And that process of breaking apart releases heat energy. So if you can gather up this material, you can concentrate it. There are also ways where you can speed up this process of it breaking apart and releasing heat. All is to say, it is a source of fuel that gets very, very hot. So the way a nuclear power plant works is you get this material that will get very, very hot, and there's one section of the nuclear power plant called the reactor. You place that uranium in the core, and you surround it by water. Oh man, is this starting to sound familiar? The nuclear material gets very, very hot. It heats up the water, and you have very, very hot, and you can pressurize it so it actually gets well above boiling point. You have incredibly hot water here. Now, that water does not actually go through the whole system. That water is contained because admittedly that water might become very radioactive and very dangerous. So if you notice, there's this pipe here that's kind of its own separate little loop. That is never going back into a river or lake or the ocean. It is its own separate thing for safety reasons. But that super hot water will actually pass through, using pipes, another sequence of water pipes. Notice this section right here. This is a totally separate set of water. The two don't mix because you don't want to mix radioactive water with cleaner water, so to speak. So I have this super hot water here, which will actually heat up another circuit, so to speak, of water. So I have water coming in here. It gets superheated because of the heat that was originally created by the uranium. Superheated water, which is highly pressurized. It can be depressurized, which will turn it to steam, which is going to spin a turbine. Now, again, we would like to have this water source right here stay as a system, as a precautionary measure. We need to therefore cool it back down so it can reheat, turn back into steam, and repeat this process. So how do we cool this water down? Well, it'll cool down slowly, but another way to do that is to have even a third set of water, say from a river or a lake. Nice cool water will pass by and it will cool down this very hot water. The very hot water, after it passes the turbine, starts to cool down, and then it will repeat its own process. The water from a river or a lake, it's passing through yet this third kind of system, this third circuit, and the way we get it to cool back down is by using very large cooling towers. Everybody, most people, when they think of a nuclear power plant, this image or something similar comes to mind. Or think of if you've ever seen the TV show The Simpsons. This is the classic image of the nuclear power plant that Homer works at. Let's be very clear, everybody. This material that is coming out of these stacks, this is just water vapor. It is steam. It is not nuclear radiation. It is not smoke. It is the same steam that comes from a kettle. It is perfectly 100% safe. There is admittedly many dangers of nuclear power plants. I'm not saying it's amazing and perfectly safe. It's not. But the idea that this is some harmful source of death is completely untrue. This is just steam. It's happening because we're cooling down that water so we can use it to keep this process going. But notice again, fundamentally, a nuclear power plant, it is creating steam, which spins a turbine, okay? Algae or biomass, you don't directly burn algae. You can use it to create oils. I believe you make oil out of it, which will also burn, or you could use crops or pieces of wood or sewage or garbage or old vegetable oil. All of these things are potentially flammable, so you burn them, you pass water in pipes nearby, that water turns to steam, that steam will spin a generator, excuse me. Okay, team, I think this is the last one we're gonna go over, solar thermal power. Let's be very clear. These are not solar panels. That's actually a different thing, and we're not going to talk about those in this video. This is using the sun, and it's using the sun's energy concentrated with mirrors. Imagine, I don't know if you've ever done this, like if you, on a sunny day, take a magnifying glass, you can concentrate the sunlight, and you can like burn things. It can be dangerous. I don't recommend you do it, but we can use this to our advantage. If it's a bright sunny day, we can use mirrors to focus and zoom in and kind of pinpoint that heat in a very specific location where there is water. That water gets superheated, it can turn to steam, and that steam will spin a turbine, okay? So again, these are not solar panels. This is using like mirrors, which can then be used to point and focus the sunlight, superheating something. Sometimes they actually use like salt rocks. We won't get into it, but ultimately what are we doing? We are heating up water, which is going to turn to steam. Everybody, all these examples, while there are power plants that are exceptions to this rule, all these types follow this idea that we're utilizing the second law of thermodynamics. We are making something very, very hot, water, which will then get turned to steam, which which will spin a turbine. That water will cool back down. We'll pass it back to the burning coal or the hot uranium in the reactor or the hot sunlight that was focused, heat it up again by utilizing the second law of thermodynamics, and that process will continue. Also, none of these processes are 100% efficient. While we want heat to be transferred on purpose, maybe imagine right here, maybe not all of this heat energy goes to the water. Some of it will heat up the tower. Some of it will miss and it'll just escape. So it's not perfectly 100% efficient. We have both usable and unusable heat flow going on. So in summary, all right, there are many types of power plants. A majority of the styles of power plants, they utilize this idea where you want to create heat, you want to produce heat in order to turn water into steam, and that steam will spin a turbine. That turbine is connected to our generator, or maybe sometimes like a generator might technically include the turbine. It doesn't really matter. But this turbine is spinning wires around magnets. We know based on our knowledge of electricity and magnetism how that will create electricity. No power plant is 100% efficient because all of them will, in ways that we just can't avoid, though we try to do the best we can, there will be some unusable heat loss, but all the examples shown in this section of slides here, they are also on purpose using the second law of thermodynamics because they are on purpose having heat transfer from some source into water. That's the second law, from hot objects to cooler material in order to create that steam and spin a turbine. Okay, so that is a wide variety of power plants in a nutshell, how they work. Notice the commonalities in them and notice how they utilize some of the physics that we've learned recently in this set of videos. Okay, that's all I got for this set. Thanks a lot for watching.